Welcome everybody. Today I will explain how to protect electronic circuits. I have total 20 tips. In this sheet you can see only 6. Remaining are in other sheets. Now first is I have connected one diode. This is 1 and 4007 in reverse. This is power supply. This is the electrolytic capacitor. This is metallized polyester capacitor. And here IC will be there or load will be there. What happens? Suppose by mistake input supply becomes reverse. By mistake we connect positive here, negative here. So without diode this IC will fail. This diode will bypass this. If this is positive, this negative, current will flow like this. And here negative voltage will not come. It will come limited to diode 0.7 volt. This capacitor helps in filtering high frequency noise or high frequency spikes here. Electrolytic capacitor will not filter high frequency because it has some inductor inside. This will filter, this will not filter. This will supply only DC current. This circuit is little better than this. I have connected one R and one diode here because if the diode reverse 0.7 also will not come. Second thing, this R and this C will act like low pass filter and high frequency component will not go this side, load side. Disadvantage of this is this point becomes unregulated because of diode drop and drop in this resistance. Because power supply current will flow in this resistor, so drop will be there. So this will not be regulated. If you can afford this, then this circuit is better than this. This is varistor, metal oxide varistor. This is the characteristics of varistor. You see, when voltage is increasing, current is 0. At certain point, it will clip the voltage. Voltage will not increase, current will increase. It will clip across this. Plus side also, minus side also. This is used in AC supply and wherever AC is there, everywhere. A good quality extension board, 230 volt extension board or 110 extension board have this MOV inside of proper size and energy. These MOV are not connected to in parallel. What happens? So this has some variation in the voltage. This clipping voltage varies, it is not fixed. Suppose one is 250, another is 260. There is some tolerance. So when voltage will come 250 volt, it will clip. Voltage will never go more than 250 and this has no use. I have the varistor. I will show you now. This is MOV. I have put one scale to measure the width of this. This is showing little more than 20 mm. Because this MOV is 20 mm size, there is a disc inside which is 20 mm in dia. Then another is written 275. It is 275 volt rating. Now another method is using transistor. Transistors are two types, AC and DC. Both are available. Mostly in electronic circuit this is used. Suppose power supply is 15 volt and IC can take maximum 25 volt. So we limit the voltage using this transistor and we select the transistor of say 20 volt. So up to 20 volt, this will not protect, but IC can take, because it can take up to 25 volt. Above 20 volt, this is, suppose surge comes. We are seeing surge here, rise time is slow and this is still slower. It doesn't come like this square wave, it comes like this. Slowly it will go up and then it will come down, and this side will be slower than this. So this is surge input without transistor. When you connect a 20 volt transistor, it will clip like this. Then this is freewheeling diode. When I switch a reactor or relay using transistor, current will flow. When you switch off this, current in reactor cannot become zero immediately. So because of this current multiplied by this open resistance of this transistor, over voltage will come. So we connect a reverse diode, that is called the freewheeling diode. When transistor is on, current will flow like this. When transistor becomes off, this current which was flowing in reactor will start flowing like this. And after some time it will become zero, because there will be power loss in this and in diode also. This diode, freewheeling diode, is must when you use DC relays. Many times they connect the diode inside of the relay itself. Now this is ferrite core. Small ferrites are available, in that we take a copper wire and make a turn like this. That becomes an inductor which protects from high frequency component. When high frequency component comes, here spikes will come. Spike may create two problems. IC may fail or IC may malfunction. It may become on-off many times, and because of on-off many times, IC itself may fail. To protect that, these core are used. These are used in power supply also and inputs also. I have a few core with me. I will show you now. These are ferrite cores. Here there is a ring. Above that, yellow color is a tape, insulation tape. Over that, copper wire turns are there, and it has become ferrite core reactor ready. This can be made in house. Here you see I have three cables. This is HDMI cable, this is USB cable, old USB cable, and this is AV cable for TV. In all three what I have, core is there. In this ferrite core, this is in both sides, wire is going from inside. In this also, wire is going from inside. In this, wire is going from inside, then there are two turns, then it goes here. I had one more cable without this ferrite core, HDMI cable. When I connected HDMI cable with TV without core, whenever I was switching some switch in my house, some lines were coming on the TV screen. Afterward I replaced with this cable which has ferrite core. Now that lines are not coming. Here I have shown one IC. Suppose IC is operating in linear range. When IC we operate in linear range, we connect two diodes here in parallel at input, plus and minus. These are 1 and 4148 diode. And here we connect a two Zener diode, maybe 5 volt or 10 volt. This diode limit the voltage across this and protect the IC. This Zener diode protect IC by not allowing IC output to go to very high. 15, suppose supply is 15 volt, in such a segment will go to 15 volt. But in this case, if our output requirement is only say 5 volt, then some 6 volt or 7 volt Zener we can connect here. Here there is a transistor, and application is just by on off. This is driver. Whenever high will come, transistor will come on, otherwise off. Here we use one resistor here. When this is not connected, this resistor will keep this 0.20 volt. Second thing, even this output is low, generally IC output will not be exactly 0 volt. It may be 0.1 volt, 0.2 volt, 0.3 volt. This will help to make the 0 volt, so transistor will remain off because no current will flow in this. This is advanced version of this. This is my favorite circuit. I have used this in more than 50 places. Here what happens, we connect a RC here. RC time constant I have shown 5 micro. You can select some other value. Because of this C, when we switch on, during this time and this time, because this is high frequency, capacitor becomes short, so more current flows. Because this is diode, this reverse diode also, so this point will not exceed 0.7 volt this side, in plus or minus, but more current will flow like this. So during this time, during on time, current flows like this. Here, current flows like this. Similarly, when you switch off, this current, negative current flows like this. The circuit completes like this. It will not go through diode, this. It will go through resistor. So this transistor will become faster on and off. Due to this fast action, transient losses in this transistor will reduce drastically. You try this circuit. Suppose you have some transistor, it is not becoming on properly, it is slow. Use this, transistor will come on faster, it will come off faster. Here we have a thyristor. This is Zener diode, this is fuse. Whenever over voltage comes, say suppose Zener diode is 20 volt. So whenever this voltage exceeds 20 volt, current will flow. The thyristor will come on, permanently on. As soon as this point and becomes get short, this will get short and fuse will blow. And this circuit is protected. This circuit operates very fast because thyristor on time is hardly 1 or 2 microseconds. I have put a diode here such that when thyristor becomes on, reverse current should not flow. Your capacitor should remain charged. This is similar to this, only difference is because here Zener voltage is not fixed. If you take 20 volt, it may be 21, it may be 19. But here, this is a comparator. If you can take a reference, say 20 volt, whenever this point supply voltage exceeds 20 volt, this will become high. There will be a driver I have not shown here, and the thyristor will trigger, and like here, it will become short and the fuse will blow. This gives more accurate protection than this. This is system protection. When we use many PCBs, in industry generally hundreds of PCBs are used. There we provide this system protection. We will have a control. We sense all voltage and current inputs and put some comparator inside. Some reference value will be there. If it is AC, it will be converted to DC. And whenever this value exceeds reference value, output will go high. This output will use to trip a relay. That is called the trip relay. And because of the trip relay, income or supply will switch off. And this whole control is protected. In all industrial control, this is used. Actually, in industry control, many big projects, for protection, there will be full panel. Not only BI, so many protection will be there, like frequency protection, voltage protection, current protection, unbalanced protection. This is number for dB by dt protection. This R and C together is called the snubber. This connected in parallel to thyristor. C is selected such that value of this impedance 1 by C omega is much higher than this. So this decides the impedance. Whenever some surge comes here, high frequency, surge will come always in high frequency way. Whenever high frequency surge comes, because the frequency is high, this impedance will become low. This impedance will become low, so it will bypass. It will reduce the dB by dt across this thyristor. Here we see CMOS IC. There are 3 CMOS IC. They are in the same PCB. This output connected to this input, this output connected to this input. But this input is coming from outside the PCB. Similarly, this output going outside the PCB. So here we connect one resistor 47 ohm or 100 ohm. Here we connect one resistor here, one here. This is 47K, this is 3.3K. Here we connect 1K if there is no other load. If load is there, this is not required. And this diode will be there inside the CMOS. What happens? When this voltage exceeds this voltage, current flow like this. And because of this 3.3K, less current will flow, so more input is allowed. And to flow this current, one return path is required. This 1K is used for return path. And this resistor is used to make this 0.0 volt. No input should be kept floating. So this resistor is connected. Similarly, output, suppose here a spice comes, to limit the current in this IC, this resistor is used. But suppose due to function you cannot use that, then you don't use. If possible, try to use. Here I have shown one IC. IC will have many inputs. Sometimes we use only say one input, D is used input. And A, B, C inputs, unused input. We don't use the inputs. Or there will be NC pins. NC means not connected pins. So this A, B, C or NC should not be left open. This input you can connect to either power supply, unused input. You can connect to ground or to another input. Similarly, NC pins which are not connected anywhere should be connected to ground. We can connect to VCC also or connect to another input. This floating input can receive the noise. Due to cluster coupling, it may transfer to other circuit. Here I have shown one optocoupler. This IC is same IC. Suppose this input, this R I have not shown here, this coming from far away place. Suppose from different room or from different building. So this will be very long. When this input wire becomes very long and goes outside the house, it may get damaged. Or some short circuit may happen. So IC will damage. But if you use the optocoupler, you see there is no connection between these and there is no electrical connection. So if some high voltage comes here, this will not pass over here. In some industrial circuits, even this wire is not going out and input is from contact, relay contacts, this optocoupler is used. Here we have ESD protection diode array. ESD means electrostatic discharge. Electrostatic discharge problem is more in CMOS. If you see the manual, it is written. Whenever we touch something, some charge will be there. Because of that charge, over voltage may come. To limit that, to protect from that discharge, electrostatic discharge, the diode array is used. This is diode array. Many, these are special diode, is not ordinary general diode, are available in array. Suppose there are two connectors, A and B, and they are connected with a longer wire. For example, this is keyboard, this is computer. Then each wire or each fan is grounded using this ESD protection diode array. This is GDT, means gas discharge tube. Gas discharge tubes are very fast and used for protection in telecom equipment from lightning impulses. Similarly, polymer ESD suppressor, ESD same. This polymer ESD suppressor are small in size and used in high speed data lines. Then this is fuse. You may be using fuse already. Fuse are two types. One is fast, one is slow. For electronic circuits, we use fast fuse. And slow type fuse are used to protect relay, motor, where inductor is there. Then this is PTC, thermistor. This is resetable type. Here what happens, when fuse blows, you have to use another fuse. But here what happens, when fault current becomes more than rated current, this will get heated up and it will get open. So no current will flow. But when current stops flowing, it will cool down after some time and it will reset. So PTC is not required to replace like fuse. Same PTC will use again and again. Today this much only. If you like the video, then please press like button and subscribe.